We're starting the lab feeling really dense, and I start out with a demo where I put a full can of Pepsi and a full can of Diet Pepsi or Coke and Diet Coke into a fish tank, and students observe that the Diet Coke actually floats to the top and the Pepsi floats to the bottom. And I use that as a launching board to sort of talk about what density is. And so where we're at right now is filling out the first page of the density lab in notes, and what I'm going to do is go over each of these questions here, and I'm going to just do that on a clean screen. So I'll try to tell you what number I'm on when I'm talking, and you can fill out your notes as you go if you miss the day. So what is density? Density is when we compare masses of different objects, but we keep their volume or their size the same. You'll notice I drew three boxes down here, all the same size, and the world is made up of particles. And so objects all have particles in them. And let's say we have 6 particles in that box, and in this box we have the same type of particle, but we have 9 particles in that one. And in this box we have 16 particles. So we had 6 in here, 9 in here, and 16 in here. And so if we took the masses of each of these objects, we can just pretend that each particle is a gram. Okay, they really wouldn't have that much mass, but we can just pretend for the sake of illustration. So pretend each particle is a gram. You would see that then this box has a mass of 6 grams. This box has a mass of 9 grams, and this box has a mass of 16 grams. But notice they're all the same size. So each of these would be 16 grams per whatever the size of this box is. Let's just call it, for the simple sake of illustration, per box. Per box. Per box. So because they're all the same size, we can compare their masses, and in this case, this is the most dense, this is the middle density, this is the least dense. So density basically is the amount of mass something has when all objects compared are the same size. Question number 2, I just took 3 boxes during class, or 3 buckets rather, and I filled one up with feathers. Another one I filled with water. And another one I filled with gold. Again, they're all the same size, but the bucket of feathers has the least mass, so the smallest mass. The one with water actually has, let me stick with the same colors here, little mass. The one with the water has the middle amount of mass, and the one with the gold has the largest mass. And again, it's the same illustration of what I talked about in number 1. All the sizes are the same, so we can then compare the masses to see which is the most dense, this being the most dense, this being the middle density, and this being the least dense. Well, it turns out you don't actually have to cut things to all the same size. Using a little math, we can cut things to the same size using math. And so to calculate density, this answers question 3 and 4. We just simply need to know 2 things. We need to know the mass of the object that we're looking at, and we need to know the volume of the object that we're looking at. And I'll explain how this sort of magically cuts things to the same size on question number 5. And so The two things, question number 3, that you need are mass and volume, and then the formula is number 4, question number 4, is density equals mass divided by volume. Question number 5. Math is pretty much a very cool thing, especially division, because we have the power to make all things equal to 1 when we divide. So in my example I've drawn here, I have some buckets and I put some particles in each one, and we're just going to pretend each particle has a mass of 1 gram. So if I took all, let's say I couldn't separate the 5 buckets for some reason. They're all attached to each other, and I can't just take one bucket off to take the mass of it. I have all 5 buckets, so I can put all 5 buckets on a balance and take the mass. And let's say we find that the buckets have a mass of 50 grams. Well, that's the mass for how many buckets? It's the mass for 5 buckets. And in my examples previously, I've been talking about comparing the mass of equal size buckets. So let's say for density, we always need to compare the mass for just one single bucket to figure out the density of an object. Well, instead of cutting that bucket off and putting it on a balance by itself, all we have to do is simply divide. And when we divide, what we end up with is equal to 10 grams for every 1 bucket. So I didn't actually have to cut the buckets in half to figure out that every bucket has a mass of 10 grams. And I tried to quickly put 10 dots in each of those buckets to illustrate that idea. And we can rewrite that as 10 grams per 1 bucket, but we don't have to write the 1, it's just understood. So this would be comparing the mass for all single buckets of something without actually having to cut buckets off of something. That's the power of division. The bottom number, when you divide, the bottom number down here always becomes a 1. So we can always figure out what 1 of something would have a mass of. Now, turns out we don't always compare things to buckets in science. In fact, the size we like to compare masses to for density is actually a centimeter cubed. So, for example, if I built a little box, we've talked about these in science a lot before, and it had a volume of a centimeter by a centimeter by a centimeter, you guys would know, multiply those together, and you would end up with a volume of 1 centimeter cubed. Well, this is the size. A centimeter cubed is the bucket we like to compare all masses to. So in science, when we talk about density, what we're doing is we're saying how much mass is in an object that is exactly this big, a centimeter cubed. So, for example, if we couldn't, let's say we had an object and we put it on a balance and the object had a mass of 100 grams. Well, to compare density, we need to know how many grams it would be if it was just a centimeter cubed. And so you could cut a chunk out of this object, that big, put that chunk on a balance, and then you would know its mass if it was 1 centimeter cubed, which is how we calculate density. But that's not very practical to be cutting things out of everything. So again, we can just use some very, very simple math to do this. We can take the volume of the entire thing, the length times the width times the height. I drew this 2-dimensionally, but I'm just going to have you assume it's 3-dimensional. And if I take the length, width, and height of it, I'll just throw some numbers up here. Say 10 centimeters by 2 centimeters. And the dimension I didn't draw going out this way, we'll say, is 1 centimeter. So you have this prism that's 10 by 2 by 1. So if I multiply all those together, I would end up with 20 centimeters cubed. Well, now I know that the mass of this is 100 grams when it's 20 centimeters cubed in size. I want to know what the mass is when it's just 1 centimeter cubed. Again, I don't have to cut the chunk out, I just divide. 100 divided by 20 is equal to 5 grams for every, the bottom number automatically always becomes a 1 when you divide. So 5 grams per 1 centimeter cubed, which is equal to 5 grams, sorry, per centimeter cubed. Sorry, the morning announcements just came on. Okay, if you understand what density is now, question number 6 should be pretty easy. If you look at the chart on page 4 of your lab, it gives some common densities. And basically every single thing listed there, for example, you look at alcohol, it says 0.79. It says cc's, but that's the same thing as a centimeter cubed, by the way. So it says grams per centimeter cubed. So if I look at that chart and I see that alcohol has a mass of 0.79 grams per centimeter cubed, or per cc, that tells me the density because it's already been cut down to 1 centimeter cubed. So for number 6, all you got to do is find gold, water, silver, and alcohol and write down the numbers you see there because those are the densities. Hey, question number 7 is just a quick reminder how you calculate volume for different types of objects. Rectangular prisms is really simple. You just simply take the length times the width times the height, and your units would end up being in centimeters cubed. For a irregular shaped object, you can't take length times width times height, but you can simply drop it into a graduated cylinder with some liquid already in it, let's say 20 milliliters, and then you put the irregular shaped object in there. The liquid level might go up to, let's say 30 milliliters, and now you know that this object is taking up 10 milliliters of space, the difference between 30 and 20. And a milliliter and a centimeter cubed are the same thing, so that's the same as 10 centimeters to the third power. And then finally, how do you take volume of a liquid? Well, that ends up being kind of a no-brainer actually. Whatever you put in your graduated cylinder is the volume. So in this case it was 10 milliliters. Okay, so that's that. And then finally, last question that you have to answer is question number 8 on your handout. And you can just carefully type in that URL and watch the Eureka number 25 video. You might be able to just go to YouTube and type in Eureka number 25, and it might come up that way also. It's on density, and you can take a couple notes about that and then summarize in your own words the rest, what density is at the bottom of the page. And for the lab, students had to calculate density of different items. It's going to be a really difficult lab for me to show you how to make up all at home, but I'm going to do the best I can. I'll probably end up putting a YouTube video on linked also, so you can try to get some of it done at home. Otherwise, you may have to spend some class time in here doing some of the makeup. So the first thing students had to take the density of was a cedar block, just a piece of wood. And you need to know 2 things to calculate density, like discussed in the notes. You need to know mass and volume. And so whenever you do your work, this is page 2 of the lab, by the way, if you're following along on the handout. When you do your work, you got to explain what to do. So you're going to get a cedar block. You're going to take its mass, just using a balance. You're going to take its volume by taking length times width times height, because it's a prism shape. And then to calculate density, you just take mass divided by volume. And so what I have here to show you is the work that I illustrated how this would be done with students. And I just made these numbers up. It wasn't actually real data from the lab, but I just did this to illustrate some points to you. So first of all, you can see I keep track of my work. I said step 1, what was done, the mass. I took it on a balance and got 35.2 grams. And I tell you what my next step is going to be. It's going to be calculate volume, and I tell you the formula I'm going to use. I make one of those boxes I've taught you how to make, where you write the formula, then you list the variables and list what you know, and then you just simply plug that into the formula, and you end up getting numbers like this. So I took the length, width, and height of the block, plug that into the formula to get the volume in centimeters cubed. And then finally, step 3 is to plug that into the density formula. Density equals mass divided by volume. And I got 0.05 grams per centimeter cubed. So this is just an example for you to see how work might be shown. This doesn't actually get written into your spot for the cedar block. Okay. So just an example. If I get a chance, I'll download those YouTubes for you, so you can kind of watch the process, and then you can keep track of it on your paper, similar to how I have done it here.